Before we explore what hydrogels are, let's look at where they already impact our lives. From contact lenses that keep our eyes comfortable to advanced wound dressings that accelerate healing, hydrogels are quietly transforming healthcare. They can also deliver drugs in a controlled manner, support tissue regeneration, enable wearable health sensors, and even remove pollutants from wastewater. So, what makes one material versatile enough to perform all these different roles? The answer lies in its unique structure and extraordinary interaction with water. Think of a hydrogel as more than just a wet sponge. It is the ultimate biointerface. These materials are three-dimensional, cross-linked polymeric networks that can absorb many times their own dry weight in water, which allows them to mimic the native extracellular matrix of our bodies. By creating this highly hydrated environment, hydrogels effectively bridge the gap between synthetic materials and living tissue, serving as a platform for everything from drug delivery to organ regeneration. But why do we need such advanced materials for something like wound healing? The reality is that traditional passive dressings often fail when it comes to chronic wounds. These wounds are complex environments, characterized by high alkaline pH, elevated levels of proteases, and persistent reactive oxygen species. A static, dry bandage just can't keep up. Instead, we need an ideal microenvironment that is adaptive, moisture-retaining, and interactive to guide a wound through the four critical stages of healing: hemostasis, inflammation, proliferation, and finally, remodeling. To build these interactive systems, we have to look at our molecular building blocks. Natural polymers like collagen and gelatin are great because they offer high biocompatibility, but they are often mechanically weak. On the other hand, synthetic polymers like PVA or PEG give us incredible tunable strength, but they lack inherent biological activity. The real magic happens when we create hybrid formulations, the best of both worlds, combining the structural integrity of synthetics with the biological instructions found in natural materials. A standout example of a natural backbone is alginate. This marine-derived polysaccharide is famous for its rapid ionic gelation, often described by the egg box model, where calcium ions sit between polymer strands to lock them into a gel almost instantly. Because of its exceptional moisture retention and ease of preparation, alginate has become a cornerstone for everything from bioprinting bases and advanced wound care to environmental filters. When we design these materials, we have to map the material properties directly to the biological timeline of healing. For instance, during the initial hemostasis phase, we need the gel to promote rapid blood clotting. As we move into the inflammatory phase, the gel needs to act like a vacuum, absorbing exudate and clearing away bacteria. During proliferation, it serves as a structural scaffold for fibroblasts to migrate across. And finally, it must undergo controlled degradation that perfectly matches the rate of new tissue growth during remodeling. One of the biggest practical hurdles is that wounds aren't flat, uniform surfaces. They are deep, irregular, and difficult to reach. This is where in situ forming hydrogels come in, which can transition from a liquid to a gel directly on the body. We can now use sprayable formulations, such as those based on Cama or Gelma, that contour perfectly to the wound bed. By using dual cross-linking mechanisms, like a quick burst of visible light combined with ionic interactions, we can stabilize these gels in seconds, ensuring complete coverage. We can take things a step further by giving these hydrogels what I like to call nanoparticle superpowers. By integrating nanoparticles directly into the matrix, we can target specific bioactivities. For example, adding zinc oxide or polydopamine nanoparticles provides potent antibacterial and hemostatic power. We've seen that adding components like L-glutamic acid can actually accelerate wound contraction, making these nanocomposite gels highly effective for treating some of the most difficult cases, like chronic diabetic wounds. The next frontier is making these materials smart. Stimuli-responsive hydrogels use dynamic polymers that react to environmental triggers, like changes in pH, temperature, or even specific enzymes. These triggers cause the gel to swell, shrink, or change color, enabling on-demand, site-specific therapeutic action. Imagine a dressing that only releases an antibiotic when it senses the high pH associated with a bacterial infection. In fact, we are now developing hydrogels that can literally communicate with us. By incorporating pH-sensitive dyes or enzyme-responsive fluorophores, these dressings provide real-time monitoring without ever having to be removed. They can detect an early infection warning and send that data directly to a smartphone, mapping out the transition from an alkaline, infected zone to an acidic, healing one. This level of control turns hydrogels into programmable therapeutic depots. They act as highly controllable reservoirs that protect delicate payloads like proteins, peptides, and even living cells from being degraded by the body too early. We can program the release of these drugs through swelling, simple diffusion, or the degradation of the matrix itself. Thermoresponsive systems are particularly exciting because they can trigger a drug release specifically when they detect the heat from an inflammation spike or a fever. It is also important to remember that these materials can heal more than just human biology. They can heal ecosystems. We are seeing hydrogels used for environmental remediation, such as removing heavy metals and dyes from wastewater, or acting as water retentive conditioners for soil in drought prone agriculture. Because these systems can be made biodegradable, they solve these problems without contributing to secondary microplastic pollution. So, if these materials are so incredible, why aren't they in every first aid kit? The commercialization bottleneck is real. Natural polymers often scale poorly due to batch variability, and there is a constant engineering trade off between achieving high mechanical strength and maintaining high water content. Furthermore, navigating the complex regulatory pathways for the FDA or CE approval of such smart materials is a long and expensive journey. Despite these challenges, the future of biofabrication is incredibly bright. We are moving toward AI guided formulations, where machine learning predicts material properties before we even hit the lab. We're seeing 4D bioprinting, where scaffolds morph their shape over time, and the use of CRISPR engineered bioinks. By integrating living cells into these advanced synthetic matrices, we aren't just covering wounds anymore. We are building the future of custom regenerative medicine.